Foi?
Então, acho que demora um pouquinho para começar. Aí foi, pode começar.
Okay. Okay, so today we'll be talking about Lex model structure for bicategories and what this means, what this comprises. Here we're talking about the model structure on the bicategory on the category of bicategories and strict functors between them. And this means that the objects will be bicategories, which are just two categories in which the composition of two morphisms is only associative up to a chosen coherent natural isomorphism. And the morphisms from a bicategory C to a bicategory D will consist of strict and two factors. This isn't in application. Sometimes this isn't usual because when the natural notion of the most used notion of morphism between bicategories is that of pseudo functors or Lex functors, and instead of strict true functors, but it's still. So we will define a bicategory. This is due to Lex. Main result here is this. Is that there is a model structure, model category on the category of Bicat strict, and so that there is a model structure here. And today we'll say a few words on what are the main structures here, which are here we'll have isofibrations of bicategories. And here we'll have biequivalences. And moreover, this model structure is cofibrillary generated. And it's proper and it's monoidal. So this is a nice model structure, and it's not hard to prove also that, as we will see, and this model structure can, as a corollary, we can have a model structure on 2cat and strict functors, which is just defined using this inclusion here, because this was saying weak equivalences, because the definition of weak equivalences and fibrations will make perfect sense both for two categories and bicategories, so the proof stays the same. And it's not hard to see that, so this will have also model structure, and that this inclusion here is a Quillen functor, is a right Quillen functor. And in fact, it's equivalent equivalence. And this is perhaps surprising, and I've seen this being mentioned. Last week, we were at the mini school of the Toposes, around Toposes event, and this was mentioned there. This usually goes mentioned like, at least if you only consider strict functors, then the theory of bicategories is homotopically equivalent to the theory of two categories. This means that, for instance, a corollary we have here is that every two category whatever bicategory here. What this actually means, right? For this equivalence, call this vector. Then exists a two category C and a bioequivalence from this include from C to B. Right, this along this inclusion factor. So every bicategory will be bioequivalent to a two category. And okay. And why are we studying this? We're studying this because we're aiming to, our goal here will be to actually study nerves of two categories of bicategories. So there is a nerve, the usual Dusky nerve is actually defined on a larger category than this one, which is strict unitary functors, two simplicial sets. And there's also like a two nerve from the same category. And this is probably the right way to see the things, is a simplicial object in cat. And the idea is to show idea is that these functors are right-killing functors. And of course, there's much more to say here, because what right-killing function with respect to what structures. Here, I think this will be respect to the Joya model structure. This isn't actually the same category that we're considering, so we have to define a model structure here. And what is a model structure here? There's a lot of work to be done. But okay. So okay, so before actually talking about the model structure on bicategories, we'll actually talk about the model structure on categories. The category of perhaps small categories. Okay, call this the canonical. This usually goes by, the name here is usually canonical model structure. Okay, so this is a model structure of course. And then the weak equivalences are equivalences. And the fibrations. The fibrations are what called isofibrations. And the reason I'm actually talking about the model structure on cat now is because it really resembles the model structure on bicategories in so many levels. In fact, it can be shown that the model structure on bicategories is induced by this model structure here, at least on 2cat. So equivalences are just fully faithful and essentially surjective functors. And isofibrations are, what is an isofibration? It's a functor from C to D with, let's follow nlab here, the functor B from E to B with the following property, that for all E upstairs over here, and for every isomorphism from PE to B, so call this phi, there exists like a morphism upstairs from E to prime, such that this is actually mapped to this phi below. How do we picture this? It's like we have this isomorphism down below here first, and we have what? We have this part here, the piece and here, and the thing is that this can actually lift to an isomorphism here. This is what's called an isofibration. Okay. And it's not hard to see that isofibrations are actually characterized by a lifting property. If you write this diagram here, and that's like, so the characterization is that P is probably a remark. Is an isofibration if every square of this shape here, here's the category with only one object, here's the category is the walking isomorphism, so it's the category with two objects and isomorphism between them. And here's B. And this property here is the same one as saying that every diagram of this form has a lift. Why is it the same thing? You have E is just selecting an object, and this will select an isomorphism below, and the cumulativity says that this isomorphism is of this shape. And the lift here will actually choose this psi such that this is satisfied. And what this means is that we can actually say that fibrations are like right lifting property against this functor here. Okay, so what are let's try to characterize all the, so let's try to characterize also the trivial fibrations. Okay, I claim this is actually very weird, but this is, what are these? These are fibrations which are equivalences. And I claim that these are surjective equivalences. Okay. Okay, so for time reasons, I'm gonna skip this. It's not hard to see. We can talk about this later. And given this, this characterization is great because now we can actually also characterize these trivial fibrations with lifting properties, and the set of generators is also finite. It considers these functors here. Actually talk about this later because it's very fun. So this is kind of neat. The first listing property here we say that the functor, like a functor here is here. This will mean surjectivity. This will mean that it is faithful. And no, that this is full, and this will be faithful. So this will characterize surjective equivalence. And given this, this is also almost a proof of the model structure. And so let's say canonical is cofibrily generated. Okay, let's just zoom out for the perspective here. So this model structure on cat, the cofibrations here are just functors injective on objects, I think, but I'm not sure. They are defined by lifting property against trivial fibrations. So we have this model structure here where we have equivalences, isofibrations, which are this property. This is characterized by a lifting property, and this is cofibrily generated. So to do the model structure on bicategories, I'm going to actually swoosh this part here. And paste it. Because it's really similar. The ideas are the same. So this model structure will be a model structure on the strict category of bicategories. And instead of equivalence, we have bi-equivalences. Instead of isofibration, we have isofibrations of bicategories. And definitions are another, but the idea here is that what is a bi-equivalence? It's a fully faithful and essentially surjective functor. And so bi-equivalence will be just the categorification of this idea, that instead of essentially surjective, will be bi-essentially surjective. Definitions are another, and also that the induced functors are equivalences. And as a fibration, the idea will be more or less the same. It will be that if you have an object and you have an isomorphism to that object below, you can lift that isomorphism, you can lift that equivalence. So let's actually define these. Let me use another color. Here. So we say that a functor f from, let me use small f from C to D, a two functor. This is the definition. Is a by equivalence if it's a pretty short definition, and this is like by essentially, the first definition is that of by essentially surjectivity, which is almost the same as essentially surjective, and for every D downstairs, there exists a C upstairs, such that there is an equivalence from FC to D. Okay, the difference here is that this is an equivalence, whereas we use on categories, this is usually an isomorphism. And this is like, and the fully faithfulness is portrayed as saying that for all C prime C, we have this component here from C prime to D FC prime, and this is an equivalence. So this is like, this generalizes essentially surjective, and this generalizes fully faithful. And you can show that, I haven't checked it, but that such a two functor has an inverse here, but the inverse is actually a pseudo functor. So leave it as this. And definition, F from E to B is an isofibration. And it's like almost the same thing. If you have a morphism from a point to another below, you have this lift. So now we have both morphisms and two morphisms. So we have to lift both things. So definition one is that if you have an object E here, so the first definition will be like ipsis literis from the definition of isofibration, replacing isomorphism by equivalence. So if you have a morphism here and an equivalence from, let's use the same notation, from P. Perhaps this is not the same as like, but it's equivalent. So, and you have a morphism like this down here, and an equivalence down here, then there exists a lift up here, such that P psi equals. So it's like the same thing, replacing isomorphism by equivalence. And the second part is like lifting the same thing, but lifting isomorphisms of two morphisms. So perhaps I will use suggestive notation, that if we have something like this, this means that this is a morphism, and we have a two functor from B, F to G, a two morphism here. Then there exists a beta upstairs, such that p beta equals alpha. So this is now an isomorphism because it's all we have. So it's really isofibration at each level that you have. Okay. So definition is clear. I didn't bring examples today, but we can certainly look for them later. And so a few remarks here, and I'll just I didn't actually, I had like a hard time with this paper. So what I'm going to bring is just a few facts on this model structure that I haven't proved, but perhaps we should prove some. So fact one, let's call that Bicat leg. So fact one, Bicat leg is cofibrantly generated. And this is expected as isofibrations were cofibrantly generated before, but the set of the generating cofibrations are actually a little bigger this time. We have like 8 generated cofibrations just for bioequivalence, for instance. And, okay, so fact two is really interesting. And that for every bicategory C, that this has a cofibrant replacement, right? Because of the model structure. So this cofibrant replacement is obtained as a factorization of the initial morphism. This morphism can be factored first as a and then as a trivial fibration. And then interesting fact is that there exists a cofibrant replacement here with the following property. The property that pseudo functors out of C, pseudo functors, will correspond to strict functors out of B. And I'm just throwing this because it is very curious. And we can perhaps talk about this after. Fact 3 is that this category is, this model structure is monoidal in the sense of monoidal model structures, but not with the Cartesian product. And this is interesting because this is actually monoidal with the gray tensor product. And while I'm not going to add all the details on the gray tensor product here, let's just say describe what is the gray tensor product for the bicategory 2, which has 2 roots, which has this let's change this. Let me just check for a second. Yeah, it's just these two categories. And well, the Cartesian product of 2 with 2 is just correspond to the usual Cartesian product, which looks like this. Right. We could, and so this commutes strictly. And there is also what Leck calls the white tensor product, or funny tensor product. This is the name at in which the category kind of looks like this, but this doesn't commute. And this it usually has a white box here. And so the gray tensor product here in the middle and this white is just a pun. It looks like this. It's like a middle term where this commutes on the nose, this doesn't commute at all, and this will commute up to a natural, up to a two-morphism necessarily in the tensor product here. That's more or less the idea. And that makes sense. This sounds like the natural, the true tensor product for Bicategories. It's actually characterized by an universal property that at least, okay, I hope this is right. I think it is. That strict functors out of the tensor product correspond to strict functors from C to pseudo functors and the last fact is, I have already talked about this, is that this is right killing. And this is not hard to see. Well, you see that definition of bicategory or biequivalence and isofibration up here. It actually makes sense for two categories with the same definition, you know, by essentially surjective, because equivalences make sense. And so, yeah, because equivalences make sense in two categories and bicategories, definitions are the same. The proof of the model structure is the same. And the fact that this is a right killing function is just saying that this is sending, this will send vibrations, equivalences, and trivial vibrations to vibrations, equivalences, and true vibrations. So it's right equivalent. And to characterize it as it's a killing equivalence, we have to show that if B, if C is cofibrant, then the unit of this could, so this has a left adjoint here, then the unit This is perhaps pointing in the wrong direction. Is and by equivalence. Again, this is not hard to show. And this is actually an implication in this direction, right? And that's it. We can open for discussion now. And what I did here was it was a very light presentation on what the model structure on by category is. It really resembles the model structure on categories. And in fact, there is a notion of, at least for two categories, right? There's the notion that if you have a model cat, then if you have some conditions here, then you have a model structure on the category of enriched categories. And for v equals to cat, this corresponds to cat here. And so the resemblance here is actually part of a general scheme of when you enrich over a category. And this goes a long way, actually. And that's it.